first thing we want to do, we're going to talk about two things, of course, that come from Euler. Okay, or making some connections here and trying to make sense of a grander story. But let's start with Euler's fantastic connection between different dimensional attributes of geometry. Okay, so that's pretty good for vertices. Oops. CES. We're going to have E for edges, and we're going to have F for faces. Now, what do these things have in common, or how do they differ? Vertices are very specifically zero-dimensional. Edges, line segments, they have length. That's it. So they're one-dimensional. And faces are two-dimensional, right? They're areas. Okay, well, you can imagine continuing this, perhaps. What Euler did is he noticed that if you take, well, we'll generalize it later. If you take a sphere and you subdivide it in some way, it turns out in any way, right? You can make any different way of breaking up the sphere, the surface of the sphere, into different combinations of vertices, edges, and faces. Well, then when you do, if you take all the vertices and add them up and write down the number of vertices, and then subtract the number of edges, and then add the number of faces, you always get 2. This is now known as the Euler characteristic. Okay, turns out anything that's homeomorphic to a sphere. So you can stretch it, and well, you can't pinch. There's the rules what you can't do, but you can stretch it as long as you keep the basic general form. But if you get a hole, then now you move to a different kind of form. It would be like a torus and so on. But for anything homeomorphic, so any kind of stretching of the sphere you want, and it's still homeomorphic to a sphere, and then you subdivide it, you're going to find this. In particular, if you take any of the Platonic solids and put them inside of a sphere and use them to subdivide the surface of the sphere, you'll find that their Euler characteristic is 2. What does this mean? They have a dimensional built-in relationship that's fixed between the numbers of their individually dimensional features. Really beautiful. And keep in mind, this is a relationship that's built in for anything that's subdividing the sphere. Now we're talking about a model of the universe that's on the outside a giant sphere. And then it is subdivided, right? So we're interested in the logic of how it gets subdivided. Okay, next step. Next step is to write down the equation for that outside sphere. This is our infinite hyperbolic construction that's applying to an infinite sphere. So we have an infinite sphere that's dividing internally hyperbolically, okay? So that perhaps a bit of a fiction because you can't get all the way to infinity, but geometrically we're allowing all the way to infinity. And if we did, it's under this hyperbolic construction specifically, what roots does it have? Well, it turns out the solutions to this, or its roots, because it's set to equal to 0, are the imaginary golden ratio, 1 over the imaginary golden ratio, the imaginary golden ratio squared, and 1 over the imaginary golden ratio squared. You notice a repeat. All of them are composed of the imaginary golden ratio in a slightly different way.
Very neat.
And in total, there's 6. 1 here in the denominator, 2 here in the denominator. A total of 6 of them arranged as roots to this infinite hyperbolic construction. That's what we're imagining. What is the features of these roots that we usually care about in algebra? If we want to take the sum of the roots, so if we take their sum, add all these together, equals 0.
Yeah.
If we take the product, equals 1. And if we take the quadrants,
it's -1.
-2.
Oh, correct.
-2. So the picture we have in our mind here is this is representing a hyperbolic internal division construction of an infinite sphere. So it's like the infinite hyperbolic construction, okay? Of course, we're going to pare down to the first quantized one. So we're not interested necessarily in the infinite one because it's not entirely accessible, but it's also less interesting than the quantized one. The quantized one's more, well, we'll get there.